All right, I think we are ready to get going here. So today, like I said, we're going to focus on exponential functions. And my first question for you is, what is it to be exponential? What does that mean? Okay, so that's a good way of looking at it. The further you go, if you're talking on the x scale, the more quickly it's going to increase. Okay, so it's a what we call it's an increasing function at an increasing rate. It increases at an increasing rate. Okay, another way to kind of look at that idea is that an exponential function is it's multiplication that gets repeated over and over again. So, like for example, let's just look at a little bit of data here that is exponential in nature. I'm going to show you what I'm talking about. Okay, so if I have my x's just go 1, 2, 3, 4, 5. Let's say my y over here is at 6. Then it's 12. Then it's 24. Then it's 48. Then it's 96, etc. You guys all catch the pattern I had going there? Okay. What's my pattern? It's doubling each time. Okay. So while up top, from one number to the next, I'm just going up plus 1, plus 1, plus 1. I'm just adding 1 each time. The pattern in my y's is a repeated multiplication. Each time I go from one to the next, I'm multiplying by 2, multiplying by 2, multiplying by 2. Okay? So that's what's going to create this exponential look to it. If I were to graph that thing, I'm not going to, but because it gets really, really large here. But it would have that exponential heading up really, really quick kind of a look to it. Okay? So if I was going to make an equation for this, or turn it into a function, okay, the exponentials are always going to be of the form a times b to the x. All right, because this little x up here, that exponent, that represents how many times you're multiplying. Okay, and b we call the base. So that's the number that you're multiplying with each time. Okay? So in this case, what's my base? 2, right? That's the number I'm multiplying over and over and over and over again. So for this one, we've got f of x equals a times 2 to the x. Okay? Then the question just becomes, what's the a? And the a we call our initial value. That's where we began. Okay? So what do you think a should be? Okay? In this case, it looks like it should be 6. It's not actually 6, though. Think about this. When you plug in a 1, what are you supposed to get out for y? Based on my data that I gave you there. Should get a 6. Okay? If this is a 6, if a were 6 and I plugged in a 1, what would I get? If a were 6 and x were 1, what would I get?
36.
No. 12. Okay? So, I'm kind of 1 removed, right? From where I should be. So, kind of take the pattern back 1 more. What should a actually be? 3. Okay? Try that now. If I have a is 3, okay, now try plugging some numbers in. If I plug in a 1, I get 3 times 2 to the first. What's that? 6. If I plug in a 2, 3 times 2 squared. which is 3 times 4, 12. It works, right? You can keep doing that. Okay? So this would be an equation that models this situation. Okay? So in general, here are some things you need to remember about piecing one of these together. The b, she said, is the base. That is the number that is getting multiplied over and over again. So the number that is repeatedly multiplied. There we go. Okay. And then the a is your initial value. Which we just need to remember is when x equals 0, not when x equals 1. Okay? So we're going to look at doing some, modeling some situations using exponential equations. And we're going to have to keep these two things straight to help us do it. Okay? So I said I was going to get to that last, but I think I'll actually go there right now because that kind of relates to what we're talking about here. So I'll give you a situation. Let's see if we can pick out what's the initial value, what's the base, and then piece together an exponential equation that'll work for that. So let's say we got a mouse population. So it begins with 20 mice. Probably shouldn't do every day. That's not realistic. Let's say how about every month? Sorry. I just want to make this thing at least seem a little realistic. So every month, let's say the population triples. So write an equation to model the population. And determine how many mice there were after a year. Okay, so this is somewhat realistic. I don't know, tripling every month, it's maybe a little high still, but a little better than every day. So we can pull out some information from this, like I said, to help build this equation, or this function, and then use that function to help us. The part that we ultimately want to know is how many are there after a year. Okay. Now, there is a way to kind of manually do this one as well, which we'll talk about. It's a valid way of doing it. But I want to focus on the function part of it too, because that's important. So, for this one, what would be our initial value of our mice population? 20. And what's our base? What are we continually multiplying that 20 by? 3, right? It triples, so we have to multiply by 3, multiply by 3. Every month we would multiply by 3 again, right? So B is 3. So this mouse population, so I'm going to use M for mice and T for time, okay? Just to get you used to using some other variables here. So M of T equals 20 times 3 to the T. Okay, so then what would I need to do with that equation to answer the question to figure out how many mice there were after a year? You'd put 12 in for T. Yep. Because T is time measured in months, right? Because that's the way I gave you the information, so you have to use it that way. So M of 12 equals 20 times 3 to the 12. It's going to be huge. What do we have? Anybody got an answer yet?
Like over a billion.
720. Just 720? It would be a lot more than 720.
I got 10,628,800. That's what I got.
Okay. So say it again. 10 million.
628,820.
Okay. So I don't know what's in the water with those mice, but stay away because there's going to be lots of them. All right, so about 10 million mice. Okay. Some other exponential type equations. So, like with populations tend to grow, so we have exponential growth. We also have exponential decay. If you guys ever worked in, or anybody taken like AP Chem or just regular chemistry, I think we probably all had at this point, right? You guys talk about half-lives in chemistry? Okay, certain elements have a half-life of a certain amount of time. Okay, so let's try something with that and use kind of the same idea. So I'm going to make up an element. Let's call it benjamonium. Has a half-life of 45 minutes. Okay, so let's stop there and make sure we understand that concept real quick. What does that mean? A half-life of 45 minutes. Every 45 minutes, there's half as much as there was. Okay, when it started. So if I started with 10 grams of benjamonium, after 45 minutes, I'd have 5 grams. And then after another 45 minutes, I'd have 2.5 grams, and et cetera, et cetera. So, okay, that's what that means. So let's say our lab contains 200 grams of benjamonium. So let's try and figure out how much is left after 400 minutes. Okay. So some of you guys are probably looking at this thing and saying, okay, I got them. I know how to do this without doing an equation. Every time 45 minutes goes past, I can just take that number and divide it by 2. And I should be able to do this without making an equation, and that'll be easy. Okay? But what's the problem here? Why can't you do that? You'd have to do it a lot of times, but not only that, does 45 go into 400? It doesn't go in evenly. So we wouldn't have a nice, neat number of times. We could probably get close, but we wouldn't know right on. Okay? Now, this mouse one we just did, that one you can, right? What could you do to kind of manually work your way through that without having to use an equation? Just think about the situation logically. You've got 20 mice. Every month, this population triples. You know you got to do it 12 months. Right. So you take your calculator and say, okay, 20 times 3. Enter. 1 time. Times 3. Enter. 2 months. Times 3. Times 3. Times 3. Can you just keep doing times 3 until you've done it 12 times and done? Right? You don't need an equation to do that. Okay? This particular one, yeah, we do. So, Now this one's a little bit trickier. I could, okay, and I want to caution you, but I could say, okay, A is 200, B is 1/2, right? Because it's a half-life, it's getting half as much each time. And I could write an equation that is f of t equals 200 1/2 to the t. Okay. But the problem with that is, what's my t measured in? No, it's not. T is not in minutes in that case. T, if I write it like this, is in increments of 45 minutes. So if t equals 1 is one 45-minute interval. T equals 2 is two 45-minute intervals. Because the half-life is not 1 minute. The half-life is 45 minutes. So every time I plug in a number for time, it's another 45-minute chunk that I'm putting onto it. Does that make sense? So it's not just straight up minutes. So that equation, like I said, I want to caution you with that because that equation is not so helpful that way. Because we want a function where we can just plug in the 400, right? And not worry about 45-minute chunks as I go along the way. So what I can do to modify that then is say, okay, I want to take 45 minutes and I want to break it down to 1 minute. What can I do with t if it's 45 minutes to bring it down to 1 minute? Say that louder. Divide it by 45. Now my time, if this is t over 45, now my time, instead of being in 45-minute chunks, is in 1-minute chunks, right? Just chop it up 45 times. Now I have an equation I can plug directly into. Okay, so this is the way I want you guys to approach these. Okay, if it's a half-life, that sort of thing. If it's not a nice, and not even just with half-life ones, but any exponential equation, if it's not a nice, neat chunk of something the way you want it, you can always divide and get it there. Okay, so in this case, now we can use f of 400, because we want to know how much is left after 400 minutes. So that's going to be 200 times 1/2 raised to the 400 over 45. Be careful typing this into your calculator. Make sure that exponent is in parentheses when you do that. Okay, so let's see what we get. It should be pretty small. 200 times 0.5 raised to the 400 over 45. Okay, so what do we end up with? Started with 200 grams, and if you round it, 0.422 looks good. You'd end up with less than half a gram after 400 minutes. So don't blink, and benjamonium's going to be gone. It's got a quick half-life. Most half-lives are measured in years. Like carbon dating, they use carbon, the half-life of carbon, which I think is like, what is it, like 4,000 years or something like that? I can't remember offhand. But it's a lot. It's a lot. So it takes a very long time to do its half-life. Okay. That's kind of the story type stuff, okay? And there's some more examples in your book that can help you with that. Here a little bit, talk about some rules for exponentials. And a lot of these you should remember from pre-calc. But it's always good to refresh it. Because when we start solving equations or working with building equations that involve exponents, these rules just have to be kind of at the tips of our fingers so that we can pull them out and use them and keep going. Because we're going to be doing a lot of work with derivatives and integrals and some other calculations down the road, and building up functions is just going to be step one. And so being able to manipulate them, simplify them, that sort of thing, we really need that utility there. So here's what we got. First of all, if A is greater than 0, and b is greater than 0. These work. And more often than not, that's what we're doing. Bases that are not greater than 0, weird things happen, and they're not technically exponential anymore. So that's why this is the case. A being greater than 0, that's just, we want an initial condition. That's something that's a positive number. Those could be negative, but more often than not, we're not dealing in situations where we're talking about negative stuff. So these two will cover most of what we've got. So number 1. So you guys remember this one? If I have a to the x times a to the y, that equals a to the what? I think somebody said it, but there was a cough and I didn't hear it. It's not xy. X plus y. You add them together. Yep. If you have the same base, you add exponents together. Number 2. Now, knowing number 1, you'll probably get this one. What if you're dividing two exponentials that have the same base? Then what? That one's a subtraction, right. So a to the x minus y. Number 3. This is called a power of a power. If I have a to the x to the y, how can I simplify that up then? I just heard it. Say it a little louder. Yeah, a to the xy. You can multiply those together. Now, equal to a to the y to the x. And sometimes we might want to do that. We might want to shuffle it around and do it the other way. Okay, but that's all the same. Doesn't matter what the order is if both of them come out to a multiplication. Number 4. This is if we have different bases, but this, I'm sorry, yeah, so that'll be an x2. So the same exponent, but different bases. Now this one is probably more of what you would expect. What do you suppose that is? AB to the x. You can combine those bases into one. All right, and then the last one, again, if you understand number 4, this one will probably make sense as well. If I'm dividing a over b to the x, then I can do both of them individually. Okay, and in that one, it kind of depends. At certain times, depending on what I'm doing, I might want to take one that's split apart and make it one fraction raised to a power, or maybe I want to go the other way with it. It kind of depends. And as we come across these things, we'll talk a little bit more about that as far as the situations where you want to go one way or the other. So just wanted to make sure that we had those written down in your notes. Those are going to be important for doing some manipulation stuff and when we kind of solve some equations with them too, which is where we're going to go next. Solving equations. So let's say I've got maybe something like that. So it's clearly exponential, right? X is in the exponent. That's kind of our red flag for this is exponential. And I've set it equal to a number, 140. So 140 is equal to my exponential function, 50 times 2 to the x. And we want to work backwards to solve for x. Okay? So let's see how much you guys remember about this. So can anybody give me a first step? What should I do? Good. Yep, divide by 50. So 140 divided by 50 is 2.8. So we get 2.8 equals 2 to the x. All right, and here's the crucial step. How do I undo an exponential? A log. Okay, so can anybody give me a log equation that I can turn this into now to help me solve it? Log base 2. And then log base 2 of what? Of what? Of the 2.8? Is that what you meant? Oh, okay. And then that's equal to x. Okay? Being able to jump back and forth from exponential to log that way is going to be important. Okay? I'm not going to reteach that whole process because we did that last year. You did it in Algebra 2. But just showing you again, that's how it all goes back and forth. And as we're solving equations, I'm just going to flip-flop between them, depending on what we're doing. Okay, now this. How do you actually calculate log base 2 of 2.8? Got a calculator, you're free to use it. How do you type it in? Anybody remember that? It kind of depends on the calculator you have. Some of the newer models will actually let you type this in exactly as you see it. And you people are lucky. If not, if you have an older calculator like mine, you have it this way. You do log 2.8 over log 2. Okay, that's called the change of base theorem. Those two logs are base 10. They're common logs. Okay, but we can turn them both into common logs and then divide because our a common log and get an answer that way. So if I do that, log 2.8 divided by log of 2, getting about 1.485. Does that sound right? We get a verification there, yeah? All right, so the solution to that equation should be 1.485. Okay. Some other types of equations, other exponentials that I'd have you solve. Let's see. Could I do? Okay, so this one is exponential. The base happens to be e, which is Euler's number. It's about 2 point, I always forget if it's 2.6 or 2.8. Oh, 2.7. Oh, it's in the middle. Okay, anyway, so it's about 2.7. It's a important. We'll discuss more later about why that is. There's actually calculus involved into why e is important. And when we get to that calculus this year, we'll talk about it, about where e comes from. But for right now, just know it's a number. It's 2.7 something something. And we can still use it to solve using logs, just like we did the last one. Okay? So let's get this one going, though. So based on how this one is set up, what do you think should be a good first step, then? Add the 21. So that's going to give us 44. Okay, then what? Divide by 2, so we got 22 equals e to the x plus 4. So what this time? Natural log, right. So natural log of 22 equals x plus 4. That's how that one would go. so then x is equal to the natural log of 22 minus 4. And a natural log your calculator can do. So that you can type in just like you see it, and we should get an answer there. So natural log 22 minus 4, and x is negative 0.9, we'll say 0.909, looks like. All right. A little bit more going on in that one. It's got a natural log as part of the process, but just remember e and natural log, they go together, and you can use that to solve those. All right, I'm going to stop there. That's, like I said, kind of the basics. You do have some more in your reading that you're going to need to pick up to help you with your homework, but that should at least get you on the right track. Okay?